Let g of x be the integral from 0 to x of f of t dt, where f is a function whose graph is shown in the figure. There are many questions here. A, B, C, D. We'll work through all of them. Each of them is pretty short in itself. Exceptionally, I've printed a copy of this question because we have a graph. So, A, estimate g of 0. So, g of 0, we just copy, since x is 0, it's the integral from 0 to 0 of f of t dt. So what is the integral from a number a to the same number a? It's always 0. We can interpret this as an area. What is the area under the graph of f here between x equals 0 and x equals 0? It's an infinitely thin slice, so there is no area. But the process of considering areas under the graph is going to be the same every time now. So g of 2 is equal to the integral. Once again, we integrate from 0 to 2 because x has been defined as being 2. So f of t dt, and this time what we need to evaluate is how much area we have here. Here it's clear 1, 2, 3, 4. We should check that the grid is actually unit squares, and it is. So we have 1, 2, 3, 4, 5, 6, and here it's an approximation, but it looks like almost like a line. So this little piece here kind of is going to fit here, and it would complete a last square. So altogether, it looks like the area under the graph between the graph and the x-axis is 7 units. G of 4 is the integral, oh I forgot the 2 here, is the integral from 0 to 4 of f of t dt. So the integral, everything we have here, all the way to 4. So we know there's already 7 there, and we have 8. These two together make 9. So the total area under the graph is 9. This is 1 more, this is 1/2, this is 1/2. G of 6, the integral from 0 to 6 of f of t dt. What happens is the integral is assigned area, so when we go beyond that x-intercept to 6, we actually have an area that we need to subtract to our integral. What is this area here? It's 1, because we can place this triangle here and it makes a square. If you want to use the equation of a triangle, base times height over 2, you will also find that it's 1, but this has to be subtracted from what we already had because it's below the x-axis. Lastly, g of 8, if we go all the way from 0 to 8, we're going to have all this positive area that we found earlier to be 9, minus 1, and minus this. And this area here is 1, 2, 3. So subtracting 3 from this number gives me g of 8 equals 5. Question B. Find the largest open interval on which g is increasing. Find the largest open interval on which g is decreasing. Well, we have a good hint here about what happens. G is increasing, and from here, g is decreasing. So where is the crucial point on the graph? The crucial point is x equals 4. As long as you move here, the area under the graph becomes greater and greater and greater. But when you reach here and you keep on moving, now you're adding some negative area. So g is going to be decreasing. So this is the key moment where g is changing from increasing to decreasing. So let's write a sentence for B. G increases on 0, 4 and decreases on 4, 8. There's only 2 intervals, so finding the largest open interval where g is increasing or decreasing, there's only one, so it's automatically the largest. Question C, identify any extrema of g. We've also kind of answered this question already. If g is increasing from 0 to 4 and then it's decreasing, then there's a maximum at x equals 4. So C, g has a maximum at x equals 4. And what is this extreme value? This is what I wrote here is not the answer to the question. The question asks, what is the extreme value? So what is the y value? It doesn't ask where is the extreme value. So what is the extreme value? The maximum of g is y equals 9. We had found it up here. Now we may also wonder about minimums. Well, we can look at all the values we have here, and it appears that the absolute minimum is y equals 0. And where does it happen? It happens at x equals 0. This one here is also a minimum. It's just a relative minimum, y equals 5 at x equals 8. So I'll just write that g has an absolute minimum of y equals 0 at x equals 0, it's the endpoint, and a relative minimum of y equals 5 at x equals 8. Now that I specified absolute and relative, I want to also add here that this is an absolute maximum, but an absolute maximum is also a relative maximum. So when it's special to be absolute, but every maximum is a relative maximum. All right, so finally question D, sketch a rough graph of G. We have plenty of points that we can place on our graph. G of 0 equals 0, G of 2 equals 7, G of 4 equals 9, G of 6 equals 8, and G of 8 equals 5. So the graph does something roughly like that. We may wonder how, if this is like a parabola, is it or not? It kind of depends on what these pieces are. If this is a line, then the integral is going to be a piece of parabola. If this is a line, then the integral is going to be a piece of parabola. This one actually does not look totally like a line, so the part here is not quite a piece of parabola. But in any case, it's not just one parabola, it's a piece, a piece, a piece, like that. And the first one here is actually a straight line because we're integrating a constant, so it's going to raise like a straight line. Now we're going to see two exercises that relate to finding the derivative of an integral. The first one is given here. So I wrote it down. There are two ways of doing that. The first one is just to go through all the calculations, because finding the integral of t squared minus 2 is quite easy. The integral of t squared minus 2 is 1/3 t cubed minus 2t, and we're integrating from -2 to x. So if now I plug in x and subtract, plugging in 2, I get 1/3 x cubed minus 2x minus, plugging in -2 here, it gives me -8/3 minus 2 times negative 2, so plus 4. Okay, so there's a mistake for the moment here because I already wrote the prime here. That's what I was looking for. So let's do it in 2 steps. I've calculated what f of x, capital F of x is. And now I want to take the derivative of this whole thing. So this is going to become x squared. The derivative of negative 2x is minus 2. And all of that is just a constant, so the derivative is 0. Here is my answer. But we saw another way of doing that. And the other way is to actually assume we know what the antiderivative is without actually calculating it. When we did that in class, we probably said that we call this f of t. In this case, it's not going to be an ideal choice because we already have a capital F which doesn't quite correspond to what we're going to do. So let's just say that this is g of t. Okay. So the goal in this exercise is to find f prime of x, which is finding the derivative of this integral. Well, what I can say is I can pretend I know what the antiderivative of t squared minus 2 is and just call it capital G of t. And I'm actually integrating, or I need to substitute x and negative 2. So this is equal to d over dx of g of x minus capital G of negative 2. And then when I take the derivative of that, it becomes the derivative of capital G of x is g of x, and the derivative of g of negative 2 is 0, because this is a constant. What you can see is we've actually, this is this step, and then this is here, minus that is here. So we're really just doing the same thing. And finally, we find that it is equal to g of x. So now I can just substitute g of t is t squared minus 2. Therefore, g of x is x squared minus 2. This is a much more powerful method, even though it's more abstract. It's more powerful because it may not be possible to find the antiderivative of t squared minus 2. When we can, it's nice, it works, but were we in a situation where we are not able to find it, we can still go through these steps. So, for the last exercise, exercise 101, we are only going to use the second method because we want to focus on a specificity of boundaries not being constant and x's. So, again, I'm going to give a name to this. This time, let's call it h of t. So when I'm looking for the derivative of capital F of x, it's the derivative of the integral of root t dt. And the integral, the antiderivative of h of t is going to be capital H of t, which I'm integrating from 0 to sine x. So, using the fundamental theorem of calculus, this is d dx h of sine x minus h of 0. The derivative of capital H of sine x is h of sine x times the inside derivative cosine x. And the derivative of negative capital H of 0 is 0 because this is just a constant. So all I have to do now is to substitute. I had h of t being this, so h of sine x is that. And there's your answer. If you want to use the first method for exercise 101, it's possible. It's obviously not very hard to find the integral of t to the 1/2 and then walk through all the steps. But it's very important to be able to also do this more abstract method because it has so much more power in difficult situations.